All right, so luckily our projector is back. We can finally come back with our recording. Before we get started, just quickly remind you on what we discussed in our last lecture regarding, the last week's arrangement. Sorry. So I did share this announcement on Canvas saying like what's our plan for week 10. Basically on week 10, I'll be here for Monday and Tuesday. Miranda, your TA, will be with you on Wednesday and Thursday. And for Friday, I'll post a pre-recorded review session of everything we discussed. Also, in addition to that, I'll be hosting office hour for Sunday the entire day, so feel free to stop by whenever you like. If the door outside the 4222 is locked, just send me an email, I'll let you in. Okay, any other questions on that regard? No? Okay, we're good. So, coming back to physical chemistry. So again, in our previous lectures, right? So in chapter 4, we discussed all the thermodynamic relations, or AKA how to calculate change of the thermodynamic state functions, delta S, delta G, delta H, delta A, etc., delta U. And then in chapter 5, we started to introduce the concept of chemical potential, and then how to use the thermodynamic table, how to calculate delta H naught or standard Gibbs free energy, change of Gibbs free energy from the table. And also we discussed how like people do experiments to get those quantities in the thermodynamic table. But at the end of the day, we as chemists, we care more about, well, what is happening at equilibrium, at chemical equilibrium? How much of my reactant is in my equilibrium mixture, how much of my product is in my equilibrium mixture. So today, hopefully, we'll be able to link the concept we discussed before, which is like thermodynamic state functions, specifically Gibbs free energy, because that's more relevant to equilibrium constant. And then also, how does the delta G of the reaction link directly to equilibrium constant? Again, this will feel a little bit like GenChem, but hopefully we're giving all the equations you learned in GenChem with a little bit more like precise definition and discussion over those terms. And also we'll look at examples that you might have done in GenChem, like the Chantelier's principle, and see when it's going to fail, right? So what's actually behind those principles that sometimes work, sometimes doesn't work. So in GenChem, people will tell you that's because of exceptions occur. And then hopefully in today's lecture and also next Monday's lecture, we'll go over what are those exceptions, like what is the physical meaning behind those exceptions of your GenChem principles, all right? So let's get started. So what do we know about reaction equilibrium? So these are the things we went over at the end of our chapter 5, where we briefly introduced reaction equilibrium. Right, so thinking about a reaction, let's say we moved everything to the right-hand side. So 0 goes to the sum of your stoichiometric coefficient times your reacting species, whether it's reactant or product. So the stoichiometric coefficient for your reactants are going to be negative. Stoichiometric coefficient for your product will be positive. What else do we know about the equilibrium? Well, so we know that at equilibrium, the sum of your stoichiometric coefficient times your chemical potential equals to 0. We also went over this derivation together, namely what we have is your dni equals to mu I dc, and then we have like dg equals to the sum of your mu I dni. And in this case, at equilibrium, we know that the Gibbs free energy, the dg, equals to 0. And some of the terms, like the stoichiometric coefficient, cannot be 0. And my dni have this dc approximated in there. So we end up having the conclusion of at equilibrium, the sum of your stoichiometric coefficient times your chemical potential must add up to 0. So these are all review of something we discussed before. And let's look at a reaction, some kind of sample reaction. Let's say we have AA plus BB goes to CC plus DD imagine this is an ideal gas reaction, meaning like everything involved in this reaction are all ideal gases. And let's look at what do we know based on our previous understanding. So a few things we know, right? So from here, from this relationship, that we can write the sum of your stoichiometric coefficient times the chemical potential equals to 0. So in this case, if we write out each of the terms, we have C times the chemical potential of C plus D times the chemical potential of D minus A times the chemical potential of A minus B times chemical potential of B equals to 0. All right. And what are these chemical potentials? So keep in mind, these chemical potentials, if we're looking at a mu C, we're saying that's a chemical potential of my species C. In this ideal gas mixture, we derived this relationship in our last lecture, saying that in the ideal gas mixture, the chemical potential of your species I equals to the chemical potential of your species I in its pure form plus RT lowering the partial pressure over the 1 bar pressure, P naught. All right, so taking these together, we can rewrite my equation 1 with all these chemical potential terms. So that becomes a little bit tedious, but we'll write it together. So it's stoichiometric coefficient C times the mu naught of your species C at certain temperature plus RT lowering partial pressure of C over P naught. Right, same for D, A, and B. So mu D naught at certain temperature plus RT lowering PD over P naught minus A times mu naught A at certain temperature plus RT lowering PA over P naught minus B times this mu B naught T plus RT lowering PB over P naught. And this will add up to be 0. Nothing fancy, we're just plugging this relationship into each of the terms in my equation A, and equation A comes from our original definition of what tells us the reaction is at equilibrium. All right. What else can we do? Now for chemical potentials of pure species, like for example these things, these are the chemical potential of your pure ideal gas A, B, C, and D. So at the end of our last lecture, we know that these mu naught of pure ideal gases are related to molar Gibbs free energy. So let's just move all of these terms into one side of the equation and leave the rest of it on the other side. And let's see how do we simplify this equation here. I'm going to write this on the board because I might want to come back to this. And I got to use the nice chalks. So that becomes, I'm just moving all the mu naught to the left-hand side and everything else left on the right. And it becomes a C mu C naught at certain temperature plus D mu D naught at certain temperature minus A mu A naught at certain temperature minus B times mu B naught at certain temperature. So this, everything these are left on the left-hand side. I'm moving everything else to the right-hand side. And this will equal to the negative RT times C ln TC over P naught plus D times ln PD over P naught minus A ln PA over P naught minus B ln PB over simply moving the terms. And let me move to the next page then. Well, so this is something we went over. So for everything on the left-hand side, these are my standard chemical potential of a pure ideal gas species A, B, C, and D. So naturally, for these pure species, we have mu naught equals to the molar Gibbs free energy of your A, B, C, and D. We went over that in our last lecture. Or the other way to put it is we can rewrite the top terms into molar Gibbs free energy, and that's going to become C times G naught, molar Gibbs free energy over temperature for species C, plus D, G naught, MT, minus A, G naught, MT, A, minus B, G naught, MTB. Or what are these things? If we write it in the form of the sum together, we're effectively summing over all A, B, and C with its stoichiometric coefficient times the molar Gibbs free energy of each species at standard state. And that just equals to the delta G naught at certain temperature. All right, and what is this? This is our standard Gibbs free energy change of the reaction. Or this is something you can calculate by reading the thermodynamic table. So that means everything on the top, this just becomes my delta G naught at certain temperature, or the standard Gibbs free energy change of the reaction. We can also simplify these terms so that it looks prettier. Yes?
Sorry, is the left side equal to that delta G naught at the temperature?
All right. And we can also simplify these equations as well. So how do we do that? Now, on the board, we have the delta G naught T equal to this long term of negative RT times C ln PC over P naught plus D ln PD over P naught, et cetera, et cetera. So what we know about the logarithm function, we have A ln X equals to ln inside X to the power of A. We also know if we're looking at ln X plus ln Y, that's effectively ln xy, or ln x minus xy is a ln x over y. So in here, instead of writing it as, yes?
Could you add parentheses to, like for the exponent?
Sure. All right, so if we want to simplify this equation, whatever on the right-hand side, we can rewrite that as negative RT ln. So whatever has a plus sign will be on the top. So that's going to be my PC over P naught to the power of C times PD over P naught to the power of D. And whatever has a negative sign will be on the bottom. So that's going to be my PA over P naught to the power of A, PB over P naught to the power of B. All right. And keep in mind, in here, inside the bracket, we're already taking the partial pressure of your species A, B, and C, A, B, C, and D, divided by the standard 1 bar of pressure. So inside the logarithm, we do not have any unit. So that's another part of the sanity check. So whenever you're writing out these things in your equilibrium constant, keep in mind your equilibrium constant, or eventually later on your reaction quotient, they are unitless things. So you want to make sure the unit cancel out. All right, so in this case, we see that all units cancel out. And in here, we define our equilibrium constant based on what's inside here. So our equilibrium constant, Kp naught, is defined as this whole thing. I'm just going to write it again with you. Right, and keep in mind, what is our reaction? Our reaction is AA plus BB goes to CC plus DD. Or the other way to put it is we can simplify our overall reaction here to be your delta GT naught equals to negative RT ln K equilibrium. Yes.
What do you mean check that it's the same unit so it all cancels out? Like if it were real numbers for the pressure inside the
Well, I guess the numeric number, the quick question answer here is numeric number doesn't matter, right? So we're taking the ratio between a partial pressure and like another pressure, which is 1 bar, or the standard pressure. So the pressure and pressure will cancel out. Now, if this one is like 1 atm, this one is 1 bar, well, it will come up with some kind of number, right? So the numeric number, that's a different dimension. We're talking about unit cancel out, and then you have the actual number to worry about. Yes.
Is KQ the same as K not P?
K equilibrium, yes.
Okay.
Well, let me actually make it more accurate. Thank you for pointing that out. All right, so this is for our, we did this derivation for this reaction of AA plus BB plus goes to CC plus DD. Obviously, we can generalize our conclusion for any kind of chemical reaction. Right, so if we want to generalize it for a reaction of 0 goes to whatsoever, sum of stoichiometric coefficient times the species AI, what do we have here? Well, similarly, we still have our delta G naught at certain temperature equals to negative RT ln Kp naught, and our Kp naught is defined as this little symbol. And if you took enough mass, this tells you that's just a product of everything after it, of your partial pressure of species I at equilibrium over the standard pressure P naught, which is 1 bar, to the power of your stoichiometric coefficient. So if it's reactant, it will be on the bottom. If it's product, it's going to be on the top. And again, the symbol just means it's a product, right? So if we look at a simple one, it's just product of AI. That just equals to like A1 times A2 all the way to AN. All right. And also like this one, thinking about rewrite it, like what if we want to write your equilibrium constant as a function of delta G? That's effectively the same as writing your Kp naught equals to the exponential of your negative delta G naught divided by RT. All right, yes.
So is A equal to that term?
No, this one I'm just trying to show like what exactly is the symbol. Yeah, so this one is just, some kind of things. Like whenever you see the symbol, it just tells you whatever goes behind that symbol are product to each other. And since we're looking at this kind of relationships, then for a specific temperature, for a specific ideal gas reactions, we can say that the Kp naught is more or less only a function of temperature. Your delta G naught is also a function of temperature for ideal gas reactions, and here you only have like over RT. So your K equilibrium, the standard equilibrium constant is only a function of temperature for ideal gas reactions. And let's do one example question together, right? So remember, the goal here today is trying to link a thermodynamic state function, which is your Gibbs free energy, in this case, the Gibbs free energy of a ideal gas reaction, to something that experimentally we can measure, or equilibrium composition. So the question can go two different ways. First way is we can give you this kind of question. We tell you, let's say we started from 0.15 mole of oxygen gas placed in a container of given volume, and equilibrium is established at 4,000 K. And we tell you that the pressure of equilibrium is 2.175 atm. Ask you to find the Kp naught and delta G naught for this reaction at 4,000 K. So this question is we start by knowing or solving for equilibrium composition. Or the other way to put it is, what is my PI equilibrium? Like, what is the partial pressure of my reactant and product at equilibrium? Use this to solve for Kp naught, the equilibrium constant at 4,000 K, or equilibrium temperature, and then use our equation of delta G naught T equals to negative RT ln Kp naught. All right, so that's the algorithm. And again, the reason I know it is by reading the question, we'll be like, okay, I know my volume, and I know like that's the initial point, so we can solve for what is the, and also we have the stoichiometric coefficient, so we can solve for what is the extent of reaction at equilibrium, knowing the pressure and also the volume. So we can solve for the equilibrium composition and use equilibrium composition to solve for the rest of the terms. So let's work on this together. Okay, I'm just gonna do it on the board. And I mean, you can find the results on the annotated note as well. So what do we know? We know that equilibrium is established at 4,000 K. We also know the pressure at equilibrium equals to 2.175 atm. And also, to make my life easier, I'm just going to rewrite that into bar, which is 2.204 bar. And we know this is an ideal gas mixture. All right. So let's just first solve. Remember, we want to solve for the equilibrium composition, or the partial pressure of each of my reactant or product in the equilibrium. So let's think about, what do we know? So first step, we know that PV equals to N total RT at equilibrium. And what do we know? We have pressure, we also have volume. So the container itself is 32.80 liter. Right, so using the PV equals to nRT, we can easily solve for the total number of species at equilibrium to be PV over RT. So plugging the numbers, I'm a little tired of plugging the numbers, but you can do it yourself. That's 0.12172 more. So that's the total number of more. And what's in my reaction mixture? I only have oxygen gas, O2, and also like elementary oxygen. So I only have two different species in my reaction mixture. So secondly, I want to solve for the extent of reaction C. So how do we do it? Well, you can do it via the ice table or whatever way you learned it in Gen Chem. I don't care how you solve it, but this is how I do it. I have my N initial of my O2 equals to 0.1500 more. And we have the reaction is a decomposition, goes into 2 oxygen gas. So my stoichiometric coefficient in front of O2 is -1. Stoichiometric coefficient in front of my elementary oxygen is 2. So I can represent my NO2 at equilibrium as 0.1500 minus the stoichiometric coefficient. And also we have the number of mole of oxygen equals to 2 times the stoichiometric coefficient. So taking together, I think I made a typo in the annotated note, by the way. Taking together, we have my N total equilibrium equals to N equilibrium of O2 plus N equilibrium of oxygen, and that equals 0.1500 plus C. All right, and that equals to my total number of mole, 2172 mole. So we can easily solve for what is the extent of reaction C by setting this up. So C equals to 0.0672 mole. And then it becomes pretty straightforward, right? We know the number of mole of my species at equilibrium. So the next step is solve for partial pressure and equilibrium constant. So the partial pressure of my oxygen at equilibrium equals to the total number of mole over the, equals to the number of mole of my oxygen, which is this one, the 0.15, over the total number of mole, which is here. And you have to translate that with the pressure. Let's see. What is my pressure there? Oh, sorry. I'm missing something. So we're talking about the partial pressure here. So that's the mole fraction of my species and times the total pressure at equilibrium. So that's the missing part. All right, and the mole fraction is something we solved, which is the number of mole of my oxygen. So that's the 0.150 minus C, and over the 0.2172, and times the total pressure at equilibrium. So that's the times 2.204 bar. And we can solve for that, and also the partial pressure of oxygen, elemental oxygen, which is the same setup. And that's just me 2C over 0.2172 times P equilibrium. All right. And then upon solving the partial pressure, obviously we can write out my Kp naught, which in this case equals to the product of my each species at equilibrium divided by P naught to the power of stoichiometric coefficient. So this one, just plug in the numbers. Just keep in mind, this one, the stoichiometric coefficient of O2 is -1. Stoichiometric coefficient of oxygen is 2. Plug in the numbers, you get the Kp naught. And at the end, we can use the delta G naught T equals negative RT ln Kp naught. Yes?
Can you remind me how you got 0.150 minus the,
This one?
yeah, like, wait, when you were first trying to find,
This one?
yeah.
All right. So this is pretty much an ICE table, right? So the initial number of mole is 0.15. In the reaction, for every C of reaction taking place, we're consuming C of O2. So stoichiometric in front of it is -1. All right.
Got it, thank you.
All right. So again, like what we're doing here, it looks super long, but effectively the things we're using are more or less just solve for the composition and then plug in to solve for partial pressure, to solve for equilibrium constant, and then delta G naught of the reaction. Some of the nice thing you can think about is, well, if this reaction is at 298 Kelvin, an ideal gas reaction, you do everything here to solve and you get a delta G naught at 298 Kelvin. You can also check that with the thermodynamic table number. They should be the same. Just a hint to say like one of the nice thing about this course. Okay, any questions on this one? All right. Obviously, this question can go the other way around as well, right? So we can give you delta G naught T. Maybe this comes from the thermodynamic table. You use it to find the equilibrium constant, and then plug it back to find the equilibrium composition as well. So the same question can go different ways as well. Next thing, for these equilibrium constants, so far we went over the equilibrium constant based on pressure. So that's where the Kp naught comes from, and thanks whoever for the reminding. So I should make it specific. So this is a pressure-based equilibrium constant. We also have, like, for example, concentration-based equilibrium constant for these ideal gas reactions. And these transformations is pretty straightforward. We can think about, like, for partial pressure, we defined it to be Pi equals Ni RT V over V for ideal gas mixtures. And if we're looking at molar concentration, your concentration Ci is defined as number of mole of your species I over the total volume. So that means we can rewrite this one by using the fact that Pi equals to Ci RT. Or we can rewrite the K naught P, or the pressure equilibrium constant, into the molar concentration equilibrium constant over the product of Ci equilibrium over a standard molar concentration to the power of stoichiometric coefficient. And typically, your standard molar concentration is defined as 1 mole per liter. All right. Okay. And, well, so far we were talking about how to convert delta G naught and equilibrium constant and the equilibrium composition. But more or less, we tend to work on systems that have different temperature. So that is, we want to derive what is the temperature dependence of my equilibrium constant, right? So we went over the equilibrium constant for ideal gas mixtures. It's only a function of temperature. But what exactly is that relationship? So that's called the Van 't Hoff equation. Let me make some space so I can write the equation we are trying to solve on the board and keep working with you on the tablet. Let's see. All right. So the equation we are trying to solve is a Van 't Hoff equation. And the final version is D ln Kp naught divided by D 1 over T equals to the negative delta H naught over R. Or the other way to put it, if we are plotting or do linear plotting of your ln Kp over 1 over T, there's a way to find out the delta H of the reaction. And let's see how that is being derived. And again, this kind of derivation question, I probably won't ask you directly on the exam, but conceptually it's important. And if similar things come up, well, you know how to approach these kind of derivation problem. All right, so let's get together. For the Van 't Hoff equation, what are we thinking about? Now, we're talking about a temperature dependence of the equilibrium constant. Right, so let's just, first of all, write my equilibrium constant as some kind of function of temperature, right? So in this case, we're rewriting or just organizing that delta G naught equals to negative RT ln Kp to say ln Kp naught equals to negative delta G naught over RT. Same thing. First thing first, Well, we're talking about temperature dependence. So it's natural to take differentiation over temperature on both ends. And that becomes d ln Kp naught divided by dt equals to this whole thing, d over dt, negative 1 over RT delta G naught. I write it this way because I know like 1 over T is something you can solve, right? But the delta G is dependent on temperature is something else we want to work on. What else do we know? Now on the right-hand side, this term here, we can rewrite it using dxy equals to x dy plus y dx. So to this point, you should trust me, like when I say our calculus is basic, it is very basic. We're still using this relationship. So we can rewrite our right side to this one, the negative 1 over RT. So I'm just saying my x is negative 1 over RT times the d delta G naught over dt plus my delta G naught over 1 over RT squared. And in here, I'm just saying like d over dt, 1 over t, negative 1 over t equals to negative 1 over t squared. Again, super straightforward differential equations. So far, so good? Now, what is this term? Right, so the right term is like, let's just leave it for now. Let's focus on this term here, which is what is my delta G naught? So in this case, what is my delta G naught? Again, my delta G naught of that certain temperature is the sum of my stoichiometric coefficient times the standard molar Gibbs free energy of each species. All right, so in ideal gas mixture, that's irrelevant. So this is the definition when we're saying this is a delta G naught of the reaction, or the standard Gibbs free energy of the reaction. And that's just the sum of your stoichiometric coefficient times the molar Gibbs free energy of each species. And what else do we know about the differential of these molar Gibbs free energy? So that goes back to our Gibbs equation. So in our Gibbs equation, we're talking about dGm equals to negative Sm dt plus Vm dp. Or the other way to put it, we can simplify this term of the delta G naught over temperature equals to, I think there's a reason I don't have temperature in there, the original one, equals to the d over dt of the sum of my stoichiometric coefficient times the molar Gibbs free energy. And since we're talking about the standard yes?
So is that ddt of delta G naught?
Yes, so this whole thing.
Oh, there's a d in this.
Thank you. And since we're talking about the standard molar Gibbs free energy, right, it's standard state. So we know that pressure is 1 bar. Or the other way to put it is we can use this relationship of dGm over dt at constant pressure equals to negative Sm. And also it comes from here, right? So when pressure is constant, your dGm just equals to negative Sm dt. So what does it mean? It means that if we're plugging this one back into the relationship here, we're getting the result of my d delta G naught over dt equals to negative sum of stoichiometric coefficient of your standard conventional molar entropy of each species, and just equals to negative delta S naught, or the standard entropy of the reaction. So far, so good? All right. And then from here, what else do we have? So going back to this original equation, right? So in here, I'm just going to copy this back down. We went over this middle part, and we can plug it in to say this equals to the negative 1 over RT times the negative delta S naught of the reaction plus delta G naught over RT square. Or if I want to take the 1 over RT square out, what we end up getting is d ln Kp naught over dt equals to 1 over RT square times delta G naught plus T delta S naught. And what is my delta G naught plus T delta S naught? That's my delta H. Or the other way to put it, we have delta G naught equals to, or in general, Gibbs free energy is defined to be H minus Ts. And in here, we're talking about delta G naught plus T delta S naught equals to delta H naught. And, well, we are one step away from our final version of the Van 't Hoff equation, which is, well, we have d ln Kp naught over dt equals to delta H naught over RT square. We also know that d 1 over T over dt equals to the negative 1 over T square. Wait, is that something wrong there? I think I'm missing my calculus a little bit here, nevertheless. So what we're trying to say is d1 over t equals to negative t squared dt. And I'll check my calculus later on if I'm wrong. And so what that means is we can simplify this term into d ln Kp naught over d1 over t, and that equals to the negative delta H naught over R. Because your t squared and t squared will cancel out in this equation. And that's our Van 't Hoff's equation. So, yes.
I did have a question about, because there's like on the annotated versions of the notes, it's like a little note about plotting the natural log of Kp versus 1 over T gives us the delta H over R. But like what is negative delta H over R? Like what is?
Oh, this one. So again,
Yeah.
what we're trying to do here is, again, we're trying to build a link between something we can measure and something that's more abstract.
Okay.
Right, so delta H naught is something that's abstract. And the equilibrium constant is something we can measure. So in our next example, and let's see how do we use it together, which is, let's think about a reaction, an ideal gas reaction of ammonia formation. And let's say in the lab, you can measure the equilibrium constant. Again, the equilibrium constant is just your composition, right? So the equilibrium constant is something you can measure if you really want. And how does that equilibrium constant change with respect to temperature? And by plotting the line Kp naught versus 1 over T, we're getting this linear regression to be equal to delta H naught over R. So this gives us a way to measure the heat of the reaction. So for this example, since I'm here, and let's see, in the actual physical chemistry lab, you might be asked to do this experiment to measure the delta H of a reaction. So in this case, let's see what it is. We're saying use this figure, which is given, to estimate delta H naught, the heat of the reaction, of the ammonia formation reaction for temperature in range of 300 to 500 K. So in this case, we're giving a very small temperature range, or the other way to put it is we know that the enthalpy will have dependency on temperature. But for such a small temperature range, we're assuming delta H naught is more or less a constant. All right, so in this question, what we're trying to do here, well, is we know that taking the differential of your ln Kp naught over 1 over T, the slope of this ln Kp naught on the y-axis. On the x-axis is 1 over T, so the slope of this curve will equal to negative delta H naught over R. So effectively, the question just asks us to find out the slope of the curve or line where the y-axis is ln Kp naught versus 1 over T. All right. And this is just a straight line. You can calculate the slope however you like. Well, I like to make my life easy by choosing a point that I know that my ln Kp naught equals to 0 and my T minus 1 is roughly equals to 0.002. It doesn't need to be exact. It's okay if you get a slightly different numeric number. And second point, let's say this one. I want to say one of them to be easy. So this is 2. So this one, I have my T minus 1 to be roughly equals to 0.0040. And my ln Kp is roughly 20. Calculating the slope, so 20 minus 0 over 0.0040 minus 0.0022, that's roughly 1.11 times 10 to the 4th Kelvin. And what is my delta H? Then my delta H naught just equals to negative R times the slope. And you can do the calculation to get a numeric number. But let's just check if the unit is fit, right? So the unit of my delta H naught is kilojoule per mole. And what's the unit of my R? My unit of my R is joule per Kelvin per mole, or kilojoule per Kelvin per mole. So if we look at the unit, kilojoule cancel out, more and more cancel out. So the slope should have a unit of 1 over Kelvin, or my slope should have unit of K, and it does. So we're happy, just to check. All right. And our next lecture, we will be talking about how to best use the Van 't Hoff's equation. And again, when we're saying this, in this equation, we're saying the delta T as small, but later on, we have also discussed that your delta H can be a function of temperature, depending on the heat capacity when the delta T range is big. So we'll see an example later on to see how to best use it. And I'll see you next Monday. And I'll post more information regarding midterm 2, probably before class next Monday, so that you have it on hand.